All right, so we will now hear the last lecture of the week on early universe cosmology.
Great. Thanks. Yes, please ask questions. Yes. I am more than happy to try to answer them in real time. OK. Good. I hope we all remember what we talked about this morning. So let's just get directly into it. So I told you at some point, and hopefully you deeply internalize this fact, that inflation has something to do with de Sitter space. Okay. De Sitter space is a maximally symmetric solution to Einstein's equations. And so you might reasonably think that the symmetries of de Sitter space can be important or useful for thinking about inflation. Okay, so that's the concept that we're going to explore in the next hour or so. Okay. Before we do this, I want to be totally clear. So the inflaton itself, the thing like driving inflation, so the inflaton definitely knows that the spacetime is not exact de Sitter, right? So inflaton is not de Sitter invariant, right? At least not linearly de Sitter invariant. One way to think about that is the inflaton, or zeta, is the Goldstone mode for breaking the de Sitter symmetries. So it better know that inflation ends at some point. Okay. Nevertheless, in certain situations, its correlation functions actually are controlled by de Sitter symmetry. You can control the weak breaking. So in particular, in slow roll inflation, where the background is very close to de Sitter space, so in so-called slow roll, the de Sitter isometries control the correlation functions of the inflaton. And for spectator fields, fields that are just around during inflation, but not the ones responsible for the background, at leading order, they respect the de Sitter symmetries, right? Because they're not the Goldstone for their breaking. Okay, so spectator fields are de Sitter invariant. Okay, this is the fine print is at leading order in slow roll. Okay. Good. All right. So just so we're clear about what the what the canvas is, what situations what we're going to discuss applies to. Okay. So let's begin by discussing the symmetries of de Sitter space. So de Sitter space can be viewed as a hyperboloid embedded in one higher dimensional space. So 4-dimensional de Sitter is the locus where x0 squared plus x1 squared plus x2 squared plus x3 squared plus x4 squared equals h inverse squared. So it's the hyperboloid of radius 1 over h squared, or 1 over h. And writing it this way makes it clear that it will be invariant under 5-dimensional Lorentz transformations. So the symmetries are SO41, which is the 5-dimensional Lorentz group. So notice this is a hyperboloid in R 1, 4. And so it has the symmetries of SO41. What are the symmetries explicitly in terms of killing vectors? So let's write them in the inflationary slicing. So remember, the inflationary slicing of de Sitter is a choice of these embedding coordinates in the 5-dimensional space, where when you pull back, the line element looks like this. Okay, and since we've been working in this coordinate patch the whole time, let's write down what the symmetry generators look like in that coordinate patch. So 6 of them are extremely obvious, right? So notice there's like an R3 factor here. And so 6 of the symmetries are just the Euclidean group of R3. They're the translations and rotations of 3-dimensional space. So let's write those down. So there are the 3-dimensional translations, di, there are the three-dimensional rotations, jij, xi dj minus xj di. Okay, and then there is one transformation that is not super obvious, but not that hard to see, which is if I rescale space and time by an overall multiple, that's a symmetry of that line element. Infinitesimally, that corresponds to doing a dilation that acts like this, eta d eta plus xi di. Okay, and then there's one, well, there are three kind of not obvious symmetry transformations, which I will just write down, but you should view them as the de Sitter analog of Lorentz boosts. Okay, or oftentimes people call them special conformal transformations for reasons that will become clear in about 5 minutes. Okay, eta d eta plus 2xj xi plus eta squared minus x vector squared delta ij dj. Okay, so these are the infinitesimal killing vectors of de Sitter. Okay, and if you get bored, which I know is like very easy to do here in Colorado, you can compute the commutators of those generators and see that indeed they satisfy an SO41 algebra. Okay, all right, so how are these generators implemented on fields in the bulk spacetime? So action on fields. So imagine we have, the simplest example is like we have a bulk scalar field in the de Sitter geometry. Its equation of motion we've written down a bunch of times, but I'll do it one more time. Equation of motion of a massive scalar takes the following form in Fourier space, phi minus 2 over eta plus, sorry, phi k prime plus k squared plus m squared over h squared 1 over eta squared phi k equals 0. Okay. So what I want to do now is I want to understand actually how the symmetries act at late times. So action on fields at late times. Right, so recall, we're interested in correlation functions at the end of inflation, right? So on the de Sitter-Penrose diagram, what we want to understand is what the consequences of symmetries are up here on the eta equals 0 surface. Okay, so to do that, so I should just say, maybe to close the loop, if I have a bulk scalar field, the way that these symmetries act is just by the Lie derivative. You just act with these differential operators on the scalar field, and that's how they act infinitesimally. And now we want to see if I push that action to late times, how it acts on fields. Okay, so let's first understand what the solutions to the wave equation look like at late times. So as k eta goes to 0, what happens is that phi of x and eta has two fall-offs. Okay, so there's something I'll call small phi of x, eta to the delta, plus some other thing, x, eta to the 3 minus delta in this case, where delta is 3 halves minus square root 9/4 minus m squared over h squared. Okay, and so I should say if you've studied like ADS CFT, this should all look pretty familiar. So what we're doing is kind of like the ADS CFT on its side. We're trying to understand how the bulk isometries act on fields at late times. Okay, and they're going to end up acting like conformal transformations. Okay, so to get the late time action, we just act with these killing vectors on the late time expansion of the field. And all that's going to really change is that every place I see derivatives with respect to time, I'm just going to pull down factors of delta and 3 minus delta. Okay, so for the time being, I'm going to assume that delta is smaller than 3 minus delta, so I can just think about this single late time fall off. Okay, so at late times, well, maybe we, I'll just write over here. All right, so at late times, okay, that same algebra of symmetries can just be written in the following way. So for the translations and rotations, nothing changes because the late time surface is translation and rotation invariant. But now we see kind of an interesting thing, which is that the dilations and special conformal transformations, which used to mix around spatial slices in the bulk interior of the spacetime, actually just map points on the boundary to each other, but rescale the fields in some interesting way. So dilation has minus delta minus xi di, and then I will not write out the details of the special conformal transformation. It's this plus some differential operator. Okay, but you can, if you just replace eta d eta with delta and set eta squared equal to 0, that's what I would have written here. Okay, these you can check still satisfy in SO41 algebra. But what's going on is this SO41 algebra is now being implemented as the conformal symmetries of the future boundary of de Sitter. Okay, and so the bulk de Sitter isometries act like conformal transformations on fluctuations of the field that survive to late times. Okay, good. All right, so then what is the consequence of de Sitter symmetry? So now if I have a de Sitter invariant correlator, right, what I need is that if I have some correlation function of phi1 to phi n, and I come through and act with the de Sitter transformation, this comes through and acts on all of the fields appearing in this correlator, right, sum over A, and I have to get 0, right? So there's this is a Ward identity. Okay, so this is what it means to be invariant under the de Sitter symmetries. Okay, all right, so that's how things act on the late time like field profiles, or equivalently, this is how things would act on the in correlators. But I've spent a huge amount of time talking about the wave function, and so we should probably understand how the symmetries act on the wave function. So action on wave function. Okay, so remember the wave function has the following representation in terms of the late time fall off of the field. So it has some kind of exponential parameterization. So dot, dot, dot. Okay, then something appears here with a kernel, psi n, phi 1 up to phi n, like this. Okay. And now if I act with one of these de Sitter transformations and ask how does it change the wave function at late times, the way it's going to change the wave function is by changing these field profiles that the wave function is a functional of. Okay, that is totally fine, but the things that we've actually been computing are these kernels. And so what we want to do is we want to integrate by parts in order to have the derivatives act on these kernels. Okay, so there's some transformation like delta phi, you march through and vary all these field profiles. But what we want to do is we want to make that transformation, which are these derivatives, act on this function of the x's. Okay, so one can do that. And what you find, if you try to do this exercise in detail or it's in the notes, what you find is that nothing really dramatic happens because the only thing in the problem that depends on x is this kernel itself. And then these operators. And so the derivatives can hit the operators, and what they will do is just generate numbers, right? So the only effect is that delta gets mapped to 3 minus delta. Okay. So the action of these generators on these wave function coefficients is exactly the same, but with delta replaced with 3 minus delta. So this transformation, delta to 3 minus delta, is often called the shadow transformation. Right. So another way of saying it is that one can interpret these kernels in the wave function as kinematically correlation functions in a conformal field theory, but where you should assign the operators of that correlation function the dual or the shadow dimension to the late time fall off of the field. Okay. All right. Then there's one additional small move, which is that the things that I wrote here are in position space. And like I said, I enjoy living in Fourier space. And so in the following, we're going to Fourier transform the operators. Right, so what we want So I'm sort of reframing the problem, right? So instead of thinking about wave function coefficients, which we like compute perturbatively, I'm saying that these objects share the kinematic properties of correlation functions of a CFT. I'm trying to be very careful with my words. They are not literally the correlation functions of like a microscopically defined CFT. They just satisfy the same word identities. Okay? And what we're going to do ultimately is we're going to try to solve the word identities viewing them as differential equations. That's where we're going. But in order to do that, we have to put them in a form that is convenient for us. And so we want to phrase the action of these generators in Fourier space. Okay, so let me just write it once and for all. So the action of the dilation operator on these wave function coefficients takes the following form. Okay, acting on the primed correlator with a momentum-conserving delta function removed, which involves some subtleties that I'm happy to discuss. So on an endpoint function, there's a factor like this: sum equals 1 to n, 3 minus delta. Okay, k dot dka, acting on 1. Okay, so this is just an example. Let me not, well, I'll write it just so we have all seen it. So similarly, the action of special conformal transformations, let me give these a hat so it's clear to differential operators, O1, On. Okay, sum minus I to delta A dka plus 2kj dkj dka minus ka, all acting on this same guy. Okay, the only reason I am going through the trouble of writing all these things out is so that you believe me that there are equations, right? So we're not going to use the equations in this kind of horrible form. We're going to obviously simplify them to the situations that we need them. But I just want to give you the impression that any object that you could be interested in, there is an equation for it, okay? It may be hard to solve, right? So if this is some very high point correlation function, I have no idea how to solve it in practice. But there is an equation that one could try to solve. Okay, that's the whole point of writing everything out explicitly. Okay, so let's solve it in situations where I can write things down in a not terrible way. Okay, so let's revisit our friend, the 2-point function. Okay, and this is already an example where, if you remember, I spent like an hour canonically quantizing a scalar field in de Sitter for you, right? And the outcome of that hour's worth of effort is that we like computed a variance of something. And we were like very happy. We were like, it's a power law, isn't that great? So let's reproduce all of that effort in like 30 seconds, okay? So for the 2-point function, the action of dilations takes the following form. So I will leave it as an exercise to you to take that horrible operator, specialize it to n equals 2, and assume that the two fields are equal. You'll find this goes like 3 minus 2 delta plus k dk. Okay, so the 2-point function on the locus of momentum conservation is just a consequence of, or a function of one momentum. And the special conformal transformation, let's write it this way. Okay, that operator, since the 2-point function is only a function of momentum magnitudes, things actually simplify quite a lot. And it turns out you can write that thing like this: dk squared plus 2 delta minus 2 over k dk. Okay, so now what are we trying to do? We're trying to find a function, right? So some function of k such that this dilation operator acting on it is 0, and this special conformal operator acting on it is 0. Fortunately, in this case, we don't really have to think that hard. A power law is going to work, right? So it turns out that this function, like O delta, is just proportional to k to the 2 delta minus 3, okay? So now let's check that this reproduces the things that we think it should. So let's check. So if we remember the zeta 2-point function, so in this language, zeta corresponds to delta equals 0. So zeta has delta equals 0. So here, to be totally honest, I am being a little bit loose about the late time field profile and the wave function and things like that. So if you translate everything appropriately, the in correlator delta, or sorry, the in correlator zeta has delta equals 0. And so we see that zeta zeta has to go like 1 over k cubed, which is this famous scale invariant spectrum. Okay. And here we got this. Okay, so there's like some pain in setting up the problem, understanding the symmetries, whatever. But once we understood that, which is totally dictated by the problem, right? There was no flexibility in doing that. Once we understood how the symmetries act on observables, the observables are totally fixed, right? So the scale invariance really is literally a consequence of the symmetries of de Sitter. At this stage, you complain that while zeta doesn't actually know that it, well, it knows that it doesn't live in exact de Sitter, but this is an example of an observable that at leading order and slow roll actually is controlled by the de Sitter symmetries. Or if it makes you feel happier, we could just talk about a massless scalar field, in which case I don't have to include any fine print. Okay, all right, so that's nice. We already reproduce some amount of annoying canonical quantization pain basically for free. Okay, good. And then you can see for yourself that if you try to do an analog of this exercise for a massive field, it actually won't be possible to reproduce the 2-point function of a massive field with a single scaling weight. You'll see that actually you need 2, okay? And that's the sort of 2 fall-offs of the field that we saw for massive fields. And so honestly, that's one of the things that makes writing down some like precise holographic dual quite hard fields in de Sitter, because it's not that a single field corresponds to a single operator like in ADS. So it's a little bit more complicated. Okay, good. All right, so one can continue to do this. So one can try to do the analogous thing for 3-point functions and reproduce some of the other things that we wrote already. You will find that there's a nice feature at 3 points, which is that even though the word identities are kind of complicated, there's actually a finite list of solutions, right? And so you can imagine enumerating all of the solutions for a given choice of representation labels. Okay, but now let me try to move on to the situation that I promised you we would think about, which is the 4-point function exchanging a massive field. Okay, any questions before I do that? Yes? Yeah, so it would be, so the translation, sorry, the question is in the massive case, what would delta be? So the translation is delta is 3/2 minus nu. Does that answer the question? Okay, okay, perfect. Other questions? Okay, yes?
Yeah, I'll ask you a quick one. Normally I would think it is CFT if I have a massive field that would break the conformal symmetry. So is a massive field?
Yeah, so the question is whether putting a mass in de Sitter breaks some of the effective conformal symmetries on the boundary. And the answer is it does not. So putting a mass in de Sitter space does not break the de Sitter symmetry. And the action of that symmetry on the boundary continues to preserve conformal invariance. What's the best way of saying it? So changing the mass here basically just changes the weight of the field, right? So the conformal dimension is the ratio of the mass in units of Hubble. And so that's a dimensionless number. It doesn't give you a scale, if you like. That's sort of the, yeah, that's why. Okay, other questions? Okay, yes?
So is this then not just dimensional analysis to get this quadratic? We have to go through the symmetries?
Well, let's see. Scale invariance kind of is dimensional analysis, right? Yes. We needed a little bit more, right? So I made some kind of like quick assumption that I didn't say very explicitly, which is that the 2 deltas appearing in this 2-point function are the same, right? And it's really there that you need the special conformal or the boost symmetry to ensure that that's true. So yeah, there would have been a small thing hanging out that there could have been a 2-point function, or there could have been mixing between fields with different masses. Yeah, does that satisfy? Okay, great. Other questions? Okay, great. All right, so let's talk about exchange of a massive particle. Okay, so if I wanted to just compute the Feynman diagram that computes this wave function coefficient, so I imagine I have some like field with generic mass, we're going to make our lives a bit simpler. We're going to put conformally coupled fields on the outside. Otherwise, things get kind of messy. And so I want to compute what the 4-point function is of conformally coupled scalars, which are kind of like simple representations in de Sitter, coming from exchanging a massive field. So this is a 4-point of conformally coupled scalars from a general mass field. Okay, if I tried to just directly do the bulk time integral, I'm not going to have a great time. And so we're going to try to calculate this thing in a slightly different way. So first we want to figure out how the conformal word identities act on this object. Okay, so let's do that. So we want to figure out what the conformal, or the, let's call them de Sitter word identities just for concreteness. Okay, they will naturally be a function of the, well, they will be derivatives with respect to the kinematic variables on which the answer depends, which will be the momenta of these external particles, K1, K2, K3, K4. It turns out it's natural to view this as a function of the perimeters of these triangles. Turns out that's like a convenient thing to do. So it ends up being useful to change kinematic variables from these momentum vectors to these ratios of side lengths, u, which I will define to be, so this ki is the length of this internal momentum, ki divided by k1 plus k2, and then v, which I will define to be ki over k3 plus k4. Okay. And a conformally coupled scalar has fall off delta equals 1, so it means that the corresponding wave function coefficient would have delta equals 2, it turns out. And so we can write the in correlator. Okay, so here I'm, yeah. Just being a bit fast, but if you're careful, you will find that this is correct. In the following form, with some f of u and v, okay? It turns out that this guy has to have mass dimension -1. And so it ends up being convenient to pull out a factor of ki. So we write this as k1 to k4, 1 over ki f hat u and v. Okay, so what we're trying to do is figure out what this dimensionless function of u and v is. Okay, good. Okay, so then one does an annoying calculation, which is one of the homework/exercises in the notes that I posted. You do this annoying calculation, and you find that the conformal word identities are equivalent to the following partial differential equation. Okay. Sorry, maybe I want to put the hats. Let's put the hats in the other way so I don't have to keep writing hat. Okay. All right, where delta u is a hypergeometric operator. Okay. All right, so what we want to do is we want to solve this PDE. And the claim is that that is equivalent to doing the bulk calculation. But of course, that can't quite be right, because this PDE has an infinite number of solutions. Right? That shouldn't really shock you, because as is well known, like 4-point functions in conformal field theories, there are an infinite number of them because they can be functions of conformal cross ratios. And so we need to figure out amongst the infinite number of solutions which one is the one we actually want. Okay, so PDE has infinite solutions. Okay, so the question is, how do we get the one we want? Okay, so now there's like some unity to all of the things that I've been telling you. So the whole reason I told you this whole story about singularities is we're going to use the structure of singularities of the answer in order to select the solution that we want from the multiplicity of solutions. Okay, so we're going to input information about singularities. Okay, so in order to explain how we're going to do that, it's useful to actually solve a simpler problem first. Okay, so let's consider a slightly simpler problem. Okay, so remember, our target is the 4-point function that comes from the exchange of something, but nothing we did actually knows that so far. So far, we've just written down the constraints of symmetries. And so any 4-point function coming from any bulk process will satisfy the same differential equation. So let's instead try to extract this solution, right? The solution where you have a contact interaction. Okay, so one way of saying that, we know that the way you tell the difference between a contact solution and an exchange solution is this contact solution has only a singularity when the energy adds up to 0. Right, so this has only total energy singularity. So we want to try to characterize the solutions to these PDEs that only have a singularity at 1 over energy. Okay, so the simplest possible one, you can actually mostly get. So the simplest contact solution, I will label it with a 0. Turns out it's just in this normalization, the internal momentum length, or the internal energy, divided by the total energy, where the total energy for me, to remind you, is K1 plus K2 plus K3 plus K4. And if I translate this into U's and V's, this is UV times U plus V. Okay? I will leave it up to you to put it into Mathematica, or ask Claude to put it into Mathematica for you to check that that satisfies that equation. Okay, but indeed, you can figure out that it does. All right, so this is a solution to that equation, and it even matches the output of a bulk calculation. So we could do this calculation. It will be exactly the same as a 4-point interaction in flat space because the interaction is Weyl invariant. And so it should just look like 1 over the total energy, which it does up to this normalization factor that we pulled out. Okay, so that's good. And then we can notice that once we have a solution, we're kind of in business. So we can use that to produce an infinite number of other solutions, right? If I act with this delta U operator on F, I'll get a new solution because delta U commutes with both delta U and delta V, right? So we can use this to construct, I'll call it FCN, which is delta U to the N acting on FC. Okay. So roughly speaking, you can ask, what are these solutions? Like, what are these infinite number of contact-like solutions that we're talking about? And you can see, if you do this explicitly, that the solution Fn kind of scales like 1 over e to the 2n plus 1. And so we see each time we act with a delta U, we're kind of increasing the power of this total energy singularity by 2. And so very roughly speaking, what's going on is acting with delta U from the bulk perspective is like acting with 2 derivatives, okay? And so what these new contact solutions we get by acting with delta are like the, say, EFT expansion, right? So for example, the simplest thing corresponds to, or the next to simplest thing corresponds to a bulk interaction of the form d phi to the 4th. Okay, so here we're already kind of building up something like a derivative expansion by finding more and more interesting solutions to this equation. Okay, good. All right, so that is the contact 4-point function. And I should say, yeah, so also if your background is kind of from the holographic side, this is quite analogous to like what HPPS did, like solving the crossing equations order by order, right? So we're kind of doing a similar type of thing. Okay, good. All right. All right, so now let's get to exchange. So tree exchange. Okay. All right, so now the exchange solution, F exchange, should have both total energy and some partial energy singularities. Okay, so how do we input that information? So now there's some like little bit of a move that will seem kind of weird, but then when I explain it, you'll say, okay, that sort of makes sense. So let's note the following thing. So we're trying to solve a PDE, but I can instead choose to solve two ODEs. So note, if we solve delta U plus mu squared. So at this level, mu squared and a quarter are just like my random choice, which will make sense in a minute. Fe equals some function, C of U and V, which we'll come back to in a sec, and the similar equation in U with the same source on the right-hand side, then this will automatically solve this PDE. This solves delta U minus delta V equals 0. Okay? There's a small condition, which is that this thing has to solve delta U minus delta V equals 0. And in fact, we want this to be a contact solution. So what I'm doing is I'm taking one of the solutions that I just found and viewing it as a source for an inhomogeneous ODE. And then the claim is the solutions to that pair of ODEs also solves this PDE. All right, so that will sound a bit magical. But let me explain what's going on. So it actually totally makes sense. So this, like from the boundary point of view or this late time conformal symmetry point of view, seems like a bit inspired. But from the bulk point of view, it's fairly obvious. What you should do is you should view this operator as basically the wave operator, right? So it's some version of box minus m squared, which when it acts on an exchange like solution or exchange correlator, what it does is it goes inside the Green's function and collapses the Green's function. So maybe it's better to just write the bulk-to-bulk propagator here. And on the right-hand side, that would give me some like I delta over square root minus g. Okay, so what's going on diagrammatically is there's some operator that when I act with it, is collapsing the internal line. Okay, and then this collapsed thing appears as a source on the right-hand side. Okay, so in a sense, like writing down this pair of ODEs is capturing something about the locality of an exchange, right? Because it's using something about the Green's function. Okay, so that's the physics of why this works. And from this point of view, you can ask, okay, what is this weird parameter that I put in? So that weird parameter is just the mass squared of the particle. Okay, and of course I labeled it in the right way so that the mass squared actually is this mu squared that we talked about when we talked about heavy particles. Okay, all right, good. All right, so now I should say, just to bring these two boards together, this pair of equations has a formal solution. Yes? Oh, sorry, sure.
So I understand philosophy, but whatever that function be, like these two choices, that's going to solve the PDE. Why do I necessarily need that the solution itself also?
Oh, you can check that if you.
Like once I solve that equation, like that f is going to be a solution to the PDE that I'm setting.
No, you can check by consistency, right? Like I have to be able to act with delta U minus delta V and get 0 on these equations. So because delta U and delta V commute with this. So the question was why this has to be a solution. But also, it's one of the exercises in the notes. So you might want to do the exercise. But yeah, that's what's going on. It's like by consistency, you have to be able to act with delta U minus delta V. Yes?
Coming back to the derivative expansion, I'm slightly confused because typically derivative expansion basically solves that.
Yeah.
Instead here it's the opposite.
It's very peculiar. So the question is why the derivative expansion is like increasing the power of energy. It's kind of a peculiarity. I don't have like a deeply insightful explanation. I will say that it is related to the fact that the effective field theory expansion in de Sitter space is a bit weird. And we can discuss it more afterwards if you want. But yes, it is a peculiarity. But it is also true. Like, you actually could just calculate like the wave function coming from that guy, and you see that it does increase the power of the total energy singularity. Maybe another way of saying it is like, you can't ever actually access this total energy singularity, and so it's not really like less soft in any meaningful sense, but if you tried to go to this pole, you see that the order is worse and worse, and it is kind of reflecting something strange about the derivative expansion, or the effective field theory expansion, which is related to what I'm about to say. But any other questions? Okay, good. All right, so I should say, these equations have a formal solution, right? Which is very similar to what we do when we like integrate out massive particles. You can imagine just inverting this operator and expanding when delta U is small compared to m squared. So there's a formal solution. Okay, so there's a formal solution where I can write F exchange as this contact source on the right-hand side divided by delta U plus m squared. This looks a bit weird, but I can also just write that as a sum of delta U over m squared to the n c, something like that. And this is some version of an EFT-like expansion, but as was just pointed out, it's kind of weird, right? Because it's a bit strange that the total energy singularity is increasing in power. And one can show that actually this is an asymptotic expansion. So the EFT expansion, at least defined in this kind of naive way, doesn't converge. Okay. The easy way to think about that is like the non-perturbative thing that is making the series asymptotic is particle production. Okay. Also happy to discuss that if people are curious. Okay. So let's think about now trying to actually solve the full problem. Okay, and we're going to take the simplest C, which is just the 1 over E contact solution. So simplest C. Then the equation we're trying to solve is the following. U squared, 1 minus U squared, du squared minus 2U cubed du plus U mu plus a quarter. Okay, acting on F equals uv over u plus v. Okay. All right, so first, so this is probably not an equation that you have run into before, okay, unfortunately. And so what that means is that we're not going to really be able to like look up the answer in a book or something. We're gonna have to figure out how this thing behaves. And so first, in that endeavor, let's try to figure out where F can be singular and what its singularities look like. Okay, singularities. Well, maybe we do it on the clipboard. Okay, and the fact that some hypergeometric operator appears tells you that somehow the answer is going to be some version of some generalized hypergeometric function, but unfortunately it's not a familiar friend. Okay, but that shouldn't stop us. We should still endeavor to try to understand its properties. Okay, great. All right, so the singularities of this guy. Okay, so notice that the source is singular if I set u to v, right? Sorry, u to minus v. Okay, so the source is singular. And the full solution will inherit that singularity. But that singularity is exactly this total energy singularity. So the limit as u goes to minus v of f, it turns out it's the flat space scattering amplitude, because this is the total energy singularity of this object, times u plus v log v. Okay, and you can actually see this directly from the differential equation without ever actually solving the differential equation. Okay, so it's another version of this thing that I keep telling you, that the total energy singularity of the object knows about flat space scattering. It's also another version of a thing I was telling you, that the singularity structure can get more interesting once you have more interesting representations. Okay, so here the singularity is a branch point. Okay. This differential operator is singular when u goes to minus 1. Right, so that's a partial energy singularity. Okay, and we can even characterize what the behavior of the solution is in the vicinity of that singularity. It turns out, you can figure out by expanding the differential operator in the limit of that singularity, that f goes like some number that I didn't write down, times the 3-point amplitude, which in this case is just a number, times a log. So there's a cut here. So again, the partial energy singularity is also a branch point, not a pole in this case. Okay. U equals 1 and u equals minus 1 are kind of treated democratically at the level of this differential operator. And so there's also a singularity when u goes to 1. This is a folded singularity. Okay, we can see again that the would-be solution as u goes to 1 scales like log of 1 minus u with some number here. And it's going to be really important that when we solve this equation, we're going to force that number to be 0, so that actually this f is singular, or sorry, is regular there. So we're going to demand that this is 0. Okay, and then finally, there's a singularity as u goes to 0. This corresponds to a collapsed configuration, which is something like this, right, where the internal line of this quadrilateral is very, very small. And in that limit, it turns out that as u goes to 0 of f, this thing scales like u to the 1/2 plus I mu plus its complex conjugate. Okay? And this is exactly this oscillatory feature that we found in the 2-point function of a massive particle. So it gets imprinted in the 4-point function in this collapsed limit. Okay. Good. All right, so I was going to, all right, so solving this full problem is a bit annoying. So let me show you that there's a simpler thing, but then I'll just write down the final answer. So if you want to get some intuition for how to deal with these types of equations, I will just set up a simpler thing that you can think about. Okay, so imagine we want to solve that differential equation. How are we going to do it? Well, unfortunately, we have to like go back to Frobenius and like find a power series expansion, stitch it together, things like that. So here's a version of that. So harmonic parable. So here's an analogous problem, but in a simpler setting. Okay, so let's imagine setting the internal energy to 0. So we set it exactly to 0, but we let the ratio u over v, which is also k12 over k34, we fix it to some number. Right, so the way that we take this limit where the internal momentum goes to 0 can depend upon the side lengths right here. Right, so there's like some ratio of the total perimeter on this side to the total perimeter on this side, which is the ratio u over v. And we can take this collapsed limit with whatever ratio we want. And we can think of the answer as a function of that ratio. So if we define xi to be u over v, then it turns out that if we define f hat as 1 over vf, then it satisfies the following equation, which is xi squared dxi squared plus mu plus a quarter f equals xi over 1 plus xi. This probably also is not a familiar friend, but if we define t is equal to log xi and f is f over square root xi, then that equation turns into the equation of a forced harmonic oscillator, where the forcing term is cosh. Okay, and so we see that the behavior, at least qualitatively, of differential equations like this are like a forced harmonic oscillator. So if you start the harmonic oscillator in its ground state and you start perturbing it, and you wait a while, it's going to have interesting admixtures of positive and negative frequency modes. Okay, and so you can solve this equation and see that in the vicinity of xi equals 0, there's some analytic solution. In the vicinity of xi equals infinity, there's some other analytic solution. But to patch them together across xi equals 1, where the two expansions break down, you need some difference of the homogeneous solution. And this homogeneous solution that you have to add to patch the two regions together is exactly representing the fact that the oscillator gets excited if you perturb it for long enough. OK, I had a dream showing you that explicitly. But let me not, because I think it will be more useful to say some things at the end. OK, good. So armed with that insight that the way we have to do things is find series solutions and patch them together, we could go back and solve the full problem. Let me just show you what the full answer looks like so that you believe it's possible. And then we'll talk about the properties of the solution. Not quite, right? Sorry, the question is whether it has something to do with resurgence. What's the right way to think? It's not infinitely unrelated. Yeah. Yeah, I mean, it is kind of related to some like Stokes phenomenon thing, if you like, right? It's like you cross the Stokes line. Yeah. OK, good. Other questions? OK, so let me just write down the full solution. So the full solution. OK, I'll write it semi-schematically. So f of u and v takes the following form, just so that you believe that there actually is such a formula. It's a double sum over two labels m and n. There are some coefficients cmn, which are ratios of gamma functions. Power series 2m plus 1, u over v to the n. This is when u over v is less than 1. And then sum mn cmn v to m plus 1, v over u, n plus pi over cosh pi mu times a homogeneous solution, which I will leave slightly abstract. And this is true for u over v bigger than 1. OK, this homogeneous solution is like a product of hypergeometric 2f1s. It's the 3-point function with a single massive particle and two conformally coupled particles, which I showed you earlier today. OK, and the way that we fix the amount of homogeneous solution we need to add is we impose the boundary conditions that the limit of the full solution as u goes to 1 is regular. And then we demand that when we go to one of these partial energy or total energy singularities, so the limit of f, let's say as u or v goes to 1, we know that this thing has to be some definite number that we can calculate times a product of logs. Right? All this is saying is we're just demanding that the solution factorizes in the way that we think that it should. So those are the two boundary conditions. One is the absence of folded singularities. The other one is some factorization property. OK. So I'm just showing you this so that you believe that there actually is a formula. I understand that I haven't given you enough information for you to totally understand the formula. But the things we care about, things like the analytic structure, I can just tell you about. So what is the analytic structure of whatever this function is? OK, I should say if you're like deep into the lore of special functions, this is some version of a Campé de Fourier function. If that doesn't mean anything to you, don't worry about it. It also doesn't mean anything to me. OK, all right. Yes, it's some horrible generalized two-variable hypergeometric function. Yes, no, I'm not sure you want to spend time with that function. OK. All right, good. All right, so what is the analytic structure? So let's look in the complex U plane. Let's draw what it looks like. So what are the interesting points? The interesting points are u equals 1, which is where there would be a possible folded singularity. Which importantly, so this is the real values of u are like physical kinematics. There's a u equals 0, which is like the collapsed limit. Maybe we get another color. OK, and then another important point is u equals -1, which is this partial energy singularity. So -1, this is partial energy. OK, and there's a cut that runs from the partial energy singularity to the collapse limit, which is the edge of the physical region. And what we've done is we've demanded that there's no singularity at the folded point. Okay, and then the total energy singularity is kind of somewhere in here at u equals minus v, so this is the total energy. Okay, and so if we take the discontinuity across this cut and evaluate it at u equals minus v, we get something related to the scattering amplitude. And notice there's this interesting feature which is quite similar to like resonances at particle colliders. So solving all the boundary conditions has enforced that there's a break point at the edge of the physical region. And so this non-analyticity at unphysical kinematics actually controls the behavior of the solution as we approach the edge of the physical region. Okay, so we can write down precisely what that looks like. So as ki goes to 0, which is this collapsed limit, you find that f takes the following form. uv over 4, 1 plus I sinh pi mu, gamma 1/2 squared, gamma minus I mu squared, over 2 pi plus complex conjugate. Okay, these are just factors. The thing I want you to focus on is this oscillatory thing. And so what we see, okay, so I'm sort of fulfilling the promise that I made to you, which is I told you that I would make this idea that having a large separation between the decay of some particle leading to an oscillatory feature precise. That's what's going on here. So we're looking at the limit where the internal particles are very, very widely separated in space. And so the internal massive particle survives for a very long time. And this oscillation is exactly the oscillation of this massive particle. Okay? We see another interesting feature that, again, what we see at particle colliders. So at particle colliders, some resonance that gets like pushed a little bit off into the complex plane leads to a bump. So that's how we see like the presence of the production of on-shell particles. Here, what's going on is some non-analyticity in the complex plane is telling us that there's an oscillatory feature as we go towards the edge of the kinematic region. Okay. The other thing I should say is, of course, the amplitude here scales like e to the minus pi mu, as promised. So this is this Boltzmann-like suppression of this feature. Okay, good. All right. Any questions about this? So I understand I did not make, partially delivered on my promise. This is like a, I think philosophically we kind of understand what's going on, but I didn't show you all of the details, but hopefully the rough idea is clear. Any questions? Yes? I'm sorry, could you? Okay, good. So the question is like, where did this solution come from? Is that a fair summary, or?
Transitioning from there to the other one, did you add
this one? Oh yeah, so this is the expansion of this mess as ki goes to 0. So this like big messy thing becomes like fairly simple in the collapse limit. Okay, so I didn't show you how to, basically this is some function that is written down in the notes, but I did not write down. Collapse limit, actually this thing dominates. This really is the homogeneous. Yes, so the question is whether I could have added a different homogeneous solution, and the answer is no. So these two boundary conditions actually uniquely fix, they fully fix the homogeneous solution. So if I added a different amount of FH, it would change one of these two things. Okay, in particular, it would change this time. Okay, does that answer the question? Yeah. Yeah, so sorry, to be clear, this is kind of uniquely fixed. I didn't write it down explicitly. I kind of gave you like a, I don't know, feel for the fact that it exists. But in the collapse limit, it has like quite explicit form, which is that. Okay, good question. Other questions? Yes?
How do I understand the fact that you start with an equation which is symmetric between u and and end up with something which doesn't stay?
Okay, good question. This question is this symmetric in U and V? The answer is secretly yes, it is. It doesn't look like it, but it is. I also haven't given you enough information for that to be verifiable or unverifiable. But in fact, that's one of the conditions on the coefficients. Could you say it one more time? Sorry. Yes. 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 I have to admit that I did not write down either of the two C's, so I don't know at this exact moment in time, but it is in the notes. So the explicit expressions for both of these are in the notes. I, off the top of my head, don't remember if they're the same. I have the impression that they are the same, actually, and what's going on is that this thing is making up the difference. But don't take my word for it. That's why I gave you very detailed notes. Other questions? Yes?
The second limit is U and V goes to -1.
I believe that is correct, but let me check real quick, sorry. Yeah, so for whatever reason, I wrote 1, but indeed it should be this singularity, so I think you're correct. Thank you. Other questions?
I think this is a non-local similarity, right? So local similarity is in the following dimension. So what's happening?
Sorry, you're asking about whether it's local or non-local? Sorry, what do you mean by non-local? You mean non-local in U and V?
I mean, in the context for the bispectrum,
Yes.
I think it's like here. This is log in K1, K3, K4, and you sometimes also have something that's not a log.
Yeah, good. So the question is whether there could be other stuff beyond this oscillatory thing. And indeed there can, right? So what I have written here is the contribution in the collapsed limit coming from an exchange with some particular choice of like cubic interaction vertex. And I've specifically written down the exchange piece. There are various things I could do. I could either choose a different cubic interaction vertex with derivatives, or I can augment this by contact interactions with derivatives. So I can then take those contact interactions and evaluate them in the collapsed limit. You can't stop me from doing that. It will not be 0, right? They will give things which are like analytic functions of U and V, right? So the point is this non-analytic thing is the signature of an exchange. So maybe to make it more clear, the analog in, so I apologize for writing on this board, but the analog in scattering amplitudes is there's like a unique s minus m squared thing. And then you can write any function of s you like. It's like s squared plus s cubed plus da, da, da. And changing the cubic interaction can be shuffled into the EFT coefficient. So this non-analytic thing is the analog of this 1 over s minus m squared pole. And then the other local things would be the analog of adding like powers of s in this exchange example. Does that, I think that's what you're asking about, right? Okay. Other questions? Yes? Okay, I will be happy to litigate the details after. I didn't give enough details for us to really have a coherent discussion about this. Here, like, this solution has been defined such that this thing has like an analytic expansion in U and V for U and V less than 1. And then we have to match that to something for U and V bigger than 1. So sort of by construction, the homogeneous mismatch only appears here. If that implies that these C's have to be different, then I'm happy with that. We can look at the explicit expressions afterwards. Yeah, I just apologize for not knowing off the top of my head what. Yeah, I didn't actually write down the full solution. I apologize. Other questions? Yes. Exactly enough time. Okay. Exactly enough time because I skipped all the details here. I apologize. But I thought it would be more interesting for us to have some like quasi-philosophical discussion. So there was another thing I wanted to say, which if you're interested in, let's just talk about offline. So here, this whole discussion has been pretty formal, right? We've been like computing things, we've been developing formalism, stuff like that. You know, the pragmatically minded amongst you may be interested in knowing what like the observational prospects of this kind of stuff are. Like, what is the actual relevance for doing this to the real world? Okay, so in keeping with the rest of the theme of these lectures, we're now going to have a like more philosophical formal discussion. But if you're interested in that like practical observational thing, come ask me afterwards. I'm happy to tell you about it. Okay, and if I had had more time, we would have both discussions. But I wanted to have this discussion because it connects a little bit to, I think, what Yara was telling you about last week. So I just want to try to bring things together a bit. Okay, and this type of stuff has, you know, consumed my life for the past few years. So I think maybe we should allow me to talk about it. Okay, all right. All right, so it's like vaguely philosophical, right? So why are we doing cosmology? Okay, so part of the reason why I'm a cosmologist, at least, is I want to understand like the origins of the universe, right? So, you know, the ultimate dream of cosmology I would say is to understand the origins of the universe. Okay, I'll just write origins, you can fill in of the universe. Okay. And what we do, like I hope I've convinced you from a very practical point of view, is like at late times we observe the correlations generated by the very early universe. And if we really want to grapple with like the emergence of things like space and time and stuff like that, it may be useful to try to like reorganize our thinking about these types of objects that we observe. Okay? And so we may want to formulate observables in some more abstract way. Okay, and I'll put a question mark here because it's unclear if this will, you know, help or not, but it's at least a useful thing to do practically. Okay, so let me try to like step by step show you how we can go from these concrete things to like a slightly more abstract world. Okay, so recall in cosmology the annoying thing was there were these vertex factors, right? And these vertex factors had powers of time, so they went like eta to the alpha or eta to the minus alpha. We can deal with, and part of the problem was integrating over these kind of annoying vertex factors. So we're going to really take the lesson of cosmology deeply to heart. We should Fourier transform everything. And so we're going to go to Fourier space to deal with these things. So I'm going to rewrite this power law. So I think here I wrote the formula with minus alpha. I'm going to write it in Fourier space. Omega to the alpha e I omega eta. Okay. This is useful because it lets me rewrite the time factors as a plane wave and then some energy. And so what that means is that at least for conformally coupled scalars, right, these eta factors shift energy. Right, so if I have a vertex factor at some place in a Feynman diagram, what it does is it kind of shifts the energies involved in that Feynman diagram. Okay, and if you follow that through, what you find is that you can write the wave function in an FRW space in terms of the wave function in flat space. So it turns out we can write wave function coefficients in FRW as energy integrals, like dx1, dxn, x1 to the epsilon, xn to the epsilon, of the flat space wave function flat. Here I'm being a bit schematic about the arguments, but it depends on some energy variables shifted by these little x's, which we then integrate over. And here, the cosmology dependence is coming from doing this interesting energy integral. Like very physically, what it's saying is like in flat space, you have some process happening. In cosmology, the background is kind of making the process happen at all possible energies. And so you should integrate over all of those energies. Okay, why is that a good thing to do? So this flat space wave function is a rational function of its arguments. Okay, so as an example, for a single exchange in flat space, this flat wave function takes the following form. So 2y over, so I'm using slightly different notation from before, so I kind of apologize. But these x's you should think of as e left and e right, morally speaking. Okay. All right, so this is some rational function. And now there's some rational function entering in an integral with some other linear factors. And so we can draw a picture of the singularities of this integral. Okay, so let me draw such a picture. So it has singularities at little x1 equals 0, little x2 equals 0. So I'm drawing the x1, x2 plane. It also has a singularity when this factor goes to 0 and these two factors go to 0. So this one is, I don't know which one is which, x1 plus y equals 0. Okay, there's one here which is x2 plus y equals 0. And then there's the singularity x1 plus x2 goes to 0. Okay, but this is amazing. So it turns out that in this picture, this wave function, the flat space wave function, is actually related to this geometric region, which is bounded by the singularities appearing in the problem. So it turns out, hopefully Yara told you about this, but this thing is the canonical form of this bounded region, right? And so there's a deep connection between this way of thinking about cosmological objects and the positive geometry and combinatorial things that Yara was telling you last week. Okay, so the reason to me that that is nice and interesting is that once we know that there's some like combinatorial structure that cosmological observables are imbued with, we can go out and start to leverage some of those combinatorial and mathematical structures both to do calculations and try to figure out new ways of thinking about these things. Okay, so this is the simplest example where you can really see some combinatorial structure appear, but you can get quite far with this kind of stuff. Like I said, this has occupied some fraction of my life for several years, and so I'm happy to obviously talk about it more if you like. Okay, this was just like a heuristic for why these types of ideas can be useful in cosmology. Okay, with that, let me say thanks for all of your attention. Thanks for all of the nice questions. I had a lot of fun. And yeah, please ask me more things. I'll be around for the rest of the day. Thanks.